I watched a movie the other day. It had a scene where an acid ate through metal. The acid just seeped right through, leaving a giant hole. It was wild. But then it made me wonder, if there are a lot of common acids around us, like vinegar and lemon juice, why don't they eat through metal like that? What makes one acid stronger than another? Let's explore. This is Real Chem. We use the word strong all the time. Strong people, strong opinions. Some of my friends even complain that my coffee is too strong. But in science, words can take on more specific meanings than in everyday life. In chemistry, strong only tells us part of the story. The other key factor is concentration. If we really want an acid to eat through metal, it helps to have an acid that is both strong and in a solution with a high concentration. Let me show you what I mean. Both strength and concentration matter for an acid's reactivity. Let's break that down with a side-by-side comparison. We'll look at two 1-molar acid solutions, one that's strong, like hydrochloric acid, that's the acid in your stomach, and one that's weak, like acetic acid, the main ingredient in vinegar that you might find in your salad dressing. Both solutions have the same 1-molar concentration of acid mixed with water, but their pH values are very different. For hydrochloric acid, the pH is about 0. For acetic acid, the pH is about 2. This difference in pH might not seem like much, but pH is a log scale, and so a 2-unit difference means 100 times fewer hydronium ions. So even though these solutions were both prepared at 1 molar concentration, the amount of hydronium ion they contain is very different. What's going on? It's all about the extent of ionization. To understand what's happening, we'll use particulate diagrams to visualize the molecules and ions in solution. In these diagrams, we let the water molecules fade into the background. The solution is almost entirely water, so there are just too many of those molecules to keep track. Instead, we'll show the water molecules as a gray background. What we're focusing on are the other key particles involved in our acid-base reaction: conjugate acids and bases, hydronium ions, and hydroxide ions. In this visualization, a 1-molar concentration of something is represented by 100 particles. This is really interesting and important. When we take a look in this way at our 1-molar solution of hydrochloric acid, we don't see 100 molecules of HCl. Instead, we see 100 hydronium ions and 100 chloride ions. That's because HCl totally ionizes. Every HCl molecule donates its proton, H+, to a water, leading to a complete conversion of HCl into hydronium and chloride ions. Now, let's compare with the 1-molar acetic acid solution. Here, we see nearly 100 acetic acid molecules. At the scale of this diagram, only one acetic acid molecule ionizes by donating its proton to a water molecule. And this produces just one hydronium ion and one acetate ion. The other 99 acid molecules remain unionized. The difference is clear. Hydrochloric acid ionizes completely, while acetic acid ionizes only a tiny amount. So we say that hydrochloric acid is a strong acid, while acetic acid is a weak acid. To demonstrate what's going on with some chemical math, we say that this difference in ionization is captured by Ka, which is the equilibrium constant for the ionization reaction of an acid. For HCl, the Ka is essentially infinite because it ionizes completely. There's no measurable amount of unionized HCl left. For acetic acid, the Ka is really small. For the sake of round numbers, we'll call it 10 to the minus 4, meaning that the reaction strongly favors the unionized form. Only a tiny fraction converts to hydronium ion in the conjugate base, the acetate ion. That's why the 1-molar solution of hydrochloric acid, the strong acid, has a pH of 0, while the same concentration of acetic acid has a pH of only about 2. pH doesn't tell the whole story. Suppose someone gave you two solutions, one of hydrochloric acid and one of acetic acid, both with a pH of about 2. You might think they must be pretty similar, but pH only tells us about the hydronium ions. When we look at all the particles in solution, we see big differences. The hydrochloric acid solution is dilute, with only a small amount of HCl present, but every molecule ionizes completely, producing hydronium and chloride ions. The acetic acid solution, on the other hand, is highly concentrated. That's because most of the acetic acid remains as unionized acetic acid molecules. Only a tiny fraction converts to hydronium and acetate ions. To get enough hydronium ions from acetic acid to make pH equal 2, the concentration of acetic acid needs to be very large, much larger than the concentration of hydrochloric acid that's needed to get to the same pH. And this highlights a key idea. pH tells us how much hydronium ion is present, but it doesn't tell us how much acid remains unionized in solution. To get a complete picture of an acid solution, we need to consider both strength and concentration. Both play an important role in establishing pH. You might think a solution of strong acid sounds scary, but remember, strong just means it ionizes completely, not that it's always dangerous. If it's dilute, its pH might be close to neutral. But if it's both strong and concentrated, break out your protective gear. That's when acids have the power to eat through metal, just like in the movies.